Hey y'all, in this lesson we are finishing up the notes on sampling distribution of sample mean, and this leads into something very important in statistics called the central limit theorem. So to demonstrate this theorem, I am going to take you to the Pearson website, which you have access to, so you can follow along. In this exercise, if you want to, I would encourage it also, because I think it will help you see some patterns. Now, I did take some screenshots of the simulations and put them in the notes so that we can kind of jot down our observations, but we are going to run a simulation here today in this lesson. So before we do that, I do want to cover a few things that we looked at in the last video, some really big ideas that were super important. One of the things we found was that when we found the sampling distribution of the sample mean, what we did was we took samples of a certain size, we found the mean of each sample, and then we took the mean of the sample means. And what did we find about that value in relation to the population mean? We found that when we did the mean of the sample means, that it was equal to the population mean. So, and then we also found we used a formula for the standard deviation. When samples were of a certain size, we used the population's standard deviation divided by square root n. So we're going to see that again today. So if you missed that video, you might go back and take a look at it. So I'm going to, share my screen really quick so I can show you the simulation. Bless you, Sergeant. And so this is Blackboard. I'm going to click on Course Home for Pearson. And then maybe it'll show up. And then I'm going to go to Tools for Success on the left and Applets here, sampling distribution. So you can do this also, you can follow along. I'm going to use a right skewed distribution. Mean and median are fine. Sample of size 2, that's okay. I'm going to stick with that. I'm going to draw 5 of those samples. So what this is finding is that's a sample of size 2. We calculated the mean and jotted it down. Sample of size 2, calculated the mean, jotted it down. So I'm going to do 5 of those, and that's our sampling distribution. Each of these little pieces represents a sample of size 2, the mean of a sample of size 2. So then I can do 5 more, and that'll give me 10 samples. And you'll kind of see we're starting to fill in this sampling distribution. It's a little hard to tell with only 10 samples, the shape. So we are going to draw, I'm going to do 1,000 in a second. I do want to show you, I want to compare the mean with the sampling distribution and the population. The population mean is about 14. The sampling distribution is 12.8, so 13. It's like kind of close, but not quite equal. And then the standard deviation is smaller, slightly smaller than the population standard deviation, because remember, to find that, we're dividing by square root n. So when you divide, it's going to make it smaller. And then this standard deviation, hold on, I've got a charger right here. Problem solved. Is based on each sample. So that's just going to vary from sample to sample. But I'm going to draw 1,000. It's not going to animate it. It'll just do it. So don't worry. And now we've populated this in. It's still right skewed, but now my mean is 13.8, which is closer. And then my standard deviation is still 8 because I still have a sample size of 2. So you can kind of draw some, you can make some observations about what's happening here whenever we draw more samples. And you can kind of make some observations in your notes as you're following along. I'll go through those in a second. In the next little picture, I drew 4,000 samples. So I'm going to do that. You can see it's getting very dense here because there's so many samples. It's still right skewed. My sample size is so small and my original population is skewed, so this is going to remain skewed. It is getting more dense. It's starting to take on a fuller shape as far as kind of looking more like a bell curve over here, but it is still right skewed. So then, let's compare. We've got, now for our mean, we've got 14, which is really 14.08 compared to 14.05. So we're getting closer to our true population mean. Even though our sample sizes are small, when we pull a whole bunch of those, we're getting closer. So now let's change one of the, one of the variables here. Let's change the sample size to 10. I'm actually going to hit reset. And I'm going to pull 1,000 of those. Hey, does that look skewed? Not really. It looks pretty normal to me. Let's pull more. Well, before we pull more, let's note the standard deviation. Now, when we had samples of size 2, our standard deviation was around 8. Now we have a sample size 10. Our standard deviation is much smaller because we're dividing by square root n. So it's going to be changing as n changes. And then our mean is close to our population mean. Let's draw, I'm just playing now, 1,000 more. Ooh, it's kind of getting narrower now. It's filling in, it's getting normal, and it's getting narrower. Pull more, more. You can see it getting taller and taller and taller. So it's populating with more samples, and it's getting more narrow because of how many samples there are. So this is an interesting concept here. We started with a right skewed graph. And when we pulled sample sizes of 10 and a whole bunch of them, our sampling distribution takes on a normal shape. That's really important. We're going to use that in a second. I'm curious. Let's do 30 here. This is not in your notes, but I'm just curious. 1,000 times. Hey, that's pretty. Look at that. Normal, all normal. So the larger the sample size, the more samples you take, the more normal and the more narrow it's going to be. And then let's see, I'm going to stop sharing, go here. So here's the notes. I've already kind of gone over the little box there. Remember that for a sample size to be large, it has to be 30 or bigger for a quantitative variable. And these are going to be quantitative variables because we're finding the mean, and you can only find the mean of numerical data. And then these are the steps. I went to My Lab Statistics, clicked on Tools for Success. I forgot to put here applets. And then I went to sampling distribution. So you can play with that yourself. You all have access to that, so you can do that. I would encourage you to do it. It's kind of fun, actually. And then I have some screenshots here. Hopefully you were kind of filling this out as we were doing it. If you didn't, I'm going to go over it real quick. So this was our first one. It is right skewed. We'll say right skewed, which means that the mean is greater than the median. And there were 10 samples of size 2. So there wasn't really enough information to really say anything about the sampling distribution. There's just not, I'm not really seeing a shape here. And this is different than the one I pulled at the beginning of the video. So if you pulled your own, if you're doing your own, yours might look a little different because we're pulling samples of size 2, but the 10 samples of size 2 that I pulled might be different than the 10 samples of size 2 that you pulled. So they're all going to be different, but the information is still the same. Still right skewed, it's still 10 samples of size 2, and we still don't have enough information to determine anything about the sampling distribution. And then in the next one, we pulled more samples, and that gave us a lot more information. We have a right skewed distribution with 1,010 samples of size 2. The means are closer. And then this standard deviation comes from standard deviation over square root n. And in this case, the standard deviation is 11.8 over square root n is 2. So if we put that in your calculator, because I don't really want to do it by hand, 11.8 over square root 2 is about 8.3. So it's close. It's a little off. There's going to be variation depending on which samples you pulled, but it's pretty close. We could round. No, we'll leave it. So we can say it's still right skewed. The what's the word? Mean is close to mu, and the standard deviation of the sampling distribution is standard deviation over square root n. And let's see, does it say mean standard deviation? Yeah. So it's kind of just jot down some things that you notice about those. Oh, I forgot to say this one is 1,010 samples of sample size 2. So more samples gave us a better picture of the sampling distribution. The sample sizes were small, so it's still right skewed, but a whole bunch of samples gives us a better picture. So let's move on to the next page. I have, again, right skewed graphs, still size 2. So even though I did 4,010 samples of sample size 2, it's still right skewed. And then the means are equal. And the standard deviation still comes from standard deviation over square root n. And n is still 2, so it's still going to be that 8.3 or 8.4, around 8. And then in the next example, I changed it from 2 to 10. And when I increased my sample size, it changed the distribution. I started with a right skewed distribution with a mean of 14 and a median of 10 or 11 if I round. I increased the sample size. I pulled a whole bunch of them, and my sampling distribution took on a normal shape. So that's really important. Sampling distribution took on a normal or approximately normal shape. There were 1,010 samples of sample size 10. And then the means were equal. And the standard deviation came from standard deviation over square root n. Our standard deviation is 11.8. Square root 10, let's type that in, see what we get. 11.8 divided by square root 10, 3.7, which is this number. Isn't that so neat? It all matches up. That's why I love math. You can always check yourself that way. So we're going to kind of summarize this down here at the bottom. When we start with a skewed graph, let's see, sorry, I'm reading this question. What conclusions can you draw about the shape of the sampling distribution that don't have a normally distributed population? So when we start with a skewed graph, when the population is skewed, whoops, if we pull a large number of samples as n increases, remember n is the size of the sample, the sampling distribution will take on, or will look roughly or approximately, whatever, normal. So when I did a whole bunch of small samples, size 2, it was still skewed. But then when I increased the sample size to 10 and I pulled a whole bunch of them, it took on this normal shape. And then when I did 30, a sample size of 30, and I did a whole bunch of those, it started getting narrow and narrower, because as n increases, the denominator is going to get bigger and bigger and bigger, which is going to make the standard deviation smaller and smaller and smaller. And that's what makes it get narrow. It kind of starts clustering up towards the population mean. So as the sample sizes and the number of samples gets bigger, we're able to zero in on the population mean, because our data is getting closer and closer and closer until you can pretty much figure out what the population mean is based on your samples, which is very exciting. My dog is sneezing, I'm sorry. And something I mentioned here, this is a really big idea. I mentioned that as n gets bigger, the denominator gets bigger and the fraction gets smaller. That's important. That's kind of an algebraic concept that I want you to focus on for a second. Let's compare, for example, 1/2, 1/3, 1/4, and 1/5. Those are easy fractions. I think my dog wants to play. That's going to be in decimal form 0.5, 0.3, 0.25, 0.2. So what is happening to the decimal number as n gets bigger? As n gets bigger, the number is getting smaller and smaller. So that's what's happening here. As n gets bigger, our fraction, which is our standard deviation, is getting smaller and smaller and smaller. It's narrowing down what our population mean is going to be. What happens to the mean and standard deviation as sample sizes get larger? The mean is going to get closer to the population mean, but the standard deviation varies from sample to sample, so it's a little hard to tell. It's going to be spread out. It's going to be pretty spread out. But when we take a look at the sampling distribution, which consists of the mean of all the samples, then that's when This is going to equal mu, our population mean, and this is going to equal the standard deviation over square root n. As n gets larger, our standard deviation of the mean, that's our sampling distribution, gets smaller. And our distribution gets narrower and normal as the number of samples gets larger and as n gets larger, kind of both and type of thing. And that's demonstrated up here with the pictures. So you can kind of see the difference here. We have a small sample size. A whole bunch of small samples is still going to result in skewed distribution. And then when we do a larger sample size and a large number of them, we're going to end up with a more normal distribution, even though we have started with skewed population. I love that. Okay, and then these, we have two normal distributions. So it starts out normal, and then I just did 10 samples of size 2. Can't really tell much there. There's not really much to see, just kind of showing that. But if you pull a whole bunch of them, I did a simulation of like, I did 1,000 and then 2,000 and then 3,000. I screenshot the 3,000. It's still normal. So even though I pulled small samples, small sample sizes, it still took on a normal distribution because I started with a normal distribution. Just because I take small samples doesn't mean that it's going to become a skewed sampling distribution. It'll stay normal. Whereas here on this page, I started with a skewed distribution. I took small sample sizes and I ended up with a skewed distribution. But over here, I started normal, I took small sample sizes, and it's still normal. So that's really important. Even though n is small, the population is normal. So the sampling distribution will also be normal. And then if you look at the means are dead on the money. 25 and 25. Darn near equal. And then the standard deviation is still going to be the population standard deviation over square root n. In this case, n is 2, and we get about 3.5. So that's where that number comes from. That's where it's always going to come from. If this had been 10, then this would be 10, and this would be smaller. It would become narrower. If this had been 30, then this would be 30, this would be smaller, and this would be even smaller. And it's going to get really tall. You're going to start seeing it get really tall like a skyscraper. So it's pretty neat. And I really encourage you to go to that applet and play with it, just so you can see for yourself how it changes, and then make some notes in your spiral or your notes or whatever. Make some observations about what's happening. As n gets bigger and bigger and bigger, the sampling distribution takes on a normal shape, roughly normal shape, and even further than that, as it gets bigger and bigger and bigger, it gets more narrow. So I'm kind of spoiling it down here. What conclusions can you draw about the shape of the sampling distributions that have a normally distributed population? It remains normal despite sample size. If it's normal, it's normal. Doesn't matter what your sample size is. And then what happens to the mean and standard deviation is the number of samples gets larger, the mean is going to equal the population mean. And then the standard deviation, as the number of samples gets larger, the standard deviation gets smaller. That's kind of math abbreviation. Infinity implies gets bigger and bigger and bigger. Negative infinity implies gets smaller and smaller and smaller. You can write that out if you prefer. It doesn't matter. And our distribution, whoops, gets narrower or skinnier. So you're going to see it's going to just get taller and taller as you get more samples. So when we start with a normal distribution, we're still going to have a normal distribution, but as we pull more and more and more samples, our normal distribution is going to take on a skinnier shape because our data is clustering. We're getting more when we're taking the mean of the sample means and we're putting them in this graph, then each data piece represents the mean of these samples. And as we pull more and more and more and more of those, they're going to cluster closer and closer and closer around the population mean, the true population mean. And so if we don't know the population mean, let's pretend like we can't figure that out because it's too big. If we pull more and more and more and more samples, then we can estimate the population mean by doing that. So if I wanted to figure out something for Ranger College and I didn't have the time to gather the data on 3,000 students, then I could pull a whole bunch of samples, you know, of size 20 or 30 or 40 or whatever. I could do 30 to be safe. Whole bunch of samples of size 30. I could find the mean of each of those samples. I could draw my little distribution, my sampling distribution of the sample means, and I could kind of guesstimate, not guesstimate, estimate where the population mean is. That's so neat. Don't you love that? I love that. I think that is so exciting. So this all leads to the whole point of the lesson. This is all very important stuff because the central limit theorem is so important, is so useful. The central limit theorem, or the CLT. This theorem ensures that even though a population may not be normally distributed, that if the sample size is relatively large, that's greater than or equal to 30, then the sampling distribution will be approximately normal. So if we had the population of an entire college or university or whatever, and maybe it's a skewed population, if I take a whole bunch of samples and I find the mean of all the samples and the samples are large enough, then my sampling distribution will be normal. All right, I'm nerding out right now, so hard. Okay, there's a few things that we need to note about the central limit theorem and sampling distributions. This is very important. Whenever you're describing a sampling distribution of a sample mean, you have to use these three things to describe it. You need to state something about the shape, which will be approximately or roughly normal. The center, which will be around the population mean. And the spread, which will be standard deviation over square root n. And you can say not very spread out or clustered around the mean, or you can use describing words like that. In the example below, we're going to use numbers to describe the spread. And then some technical conditions that have to be met before you can apply the central limit theorem are the samples must be randomly selected. The sample size must be large. If it is not large, then the population must be normal. If the population is normal to begin with, then the shape of the sampling distribution will also be normal. If the shape is not necessarily normal, as long as the number of samples or the sample size is large enough, the sampling distribution will be, approximately normal. This is, I said this backwards, if the sample size, sorry about that, that's a little typo. If the sample size is large enough, then the sampling distribution will be approximately normal. We saw that back here. My sample size of 2 resulted in a skewed, and a sample size of 10. That's actually still not normal, but I pulled so many of them, not normal, not large enough, but I pulled so many of them that it came out normal. So it's kind of a both. All right, so I have an example here. I want you to pause it and try it. When it says, what's it say? Identify the sampling distribution. What it's asking for is for you to describe the sampling distribution. So go ahead and try both of those and then come back and check your work. Oops. So on the first one, since the variable is normally distributed, we say that the sampling distribution is also normal, which means it's bell-shaped with a mean of 100 and a standard deviation of 4. And I got the 4 from doing the standard deviation divided by square root n, where n is 49. So I have described the sampling distribution. I have the shape, I have the mean, and I have the standard deviation. So that's all of it. And the next one, it says, can you determine the sampling distribution of the sample mean for samples of size 16 if the distribution of the variable under consideration is unknown? So we don't know if it's normal or not, and the sample size is 16. Is the sample size large enough to determine whether anything about it, the sampling distribution? No. Sample size is too small and it might be skewed. So we can't determine anything about the sampling distribution. We can't use the central limit theorem, which would allow us to determine something about the sampling distribution, because the sample size is not large enough and we don't know if the population is normal. If they had said the population is normal, then we could use the sample size of 16 to draw conclusions. But since we don't know if it's normal, then we can't draw conclusions. Likewise, if this had been large, even if it were skewed, since it's large enough, we can draw conclusions. But it's not. It's not either of them. You have to meet one of the conditions. It either has to be large enough or it has to be normally distributed. So no, because the sample size is not large and the distribution of the population might be skewed. We don't know. If it were normal, we could proceed, but we don't know. So that is all. This page, this information is all very important. So I would encourage you to please go play with that applet and just kind of get your bearings about it so you can draw your conclusions and understand where this is coming from. These technical conditions are very important. They have to be met. When you're describing things, you have to use those 3 describing measures. But that's all I have for this lesson. I hope you enjoyed it. I hope you learned something from it. If you have any questions, please let me know and I'll be more than happy to help.